Thank you.
감사합니다.
It's a great honor to come to Korea, which is no secret is a very important nation in the nuclear story. I hope some useful things to say. Public image of nuclear energy has been demonized over the last 70 years. The urgent need to respond to climate change, that such attitudes have got to be reconsidered, not just technically, but culturally and historically. The universe is absolutely vast and extremely old, but we are only here for a short time, each of us. As nature's guests, she asks us to do three things. One is study how things work. Secondly, to leave the place as we found it. And thirdly, to cooperate with other guests socially. But energy is a problem. We have no life without energy. And where can we find enough of it and to enjoy life while we're here? In the past 70 years, we've neglected these three rules, and our children should do better than we have done. We must not overreact through fear and excitement. So, when domesticating fire years ago, man taught his children to understand too and to obey the rules. We should remember the same when we look at other forms of energy. In this way, man gained superiority over other creatures that didn't learn to use rules and to understand. Mary Curie said, "Nothing in life is to be feared, it is to be understood." Adam Smith, the 17th century economist, wrote that fear and excitement should be controlled by natural science. He said, "Science is the great antidote to the poison of enthusiasm and superstition." But we should distinguish between natural science, that is how nature works, and technology, that is what man may do with it, putting science to work. Technology should not try to overcome the boundaries of natural science because it will fail. But imagination is extremely important, although the truth can be hard to establish. In medicine, it is well known that patients who think they have been treated when they have not have an improved rate of recovery. This is what is called the placebo effect. The nocebo effect occurs when people think that they have been harmed or injured when they have not. News that you have been irradiated and there's a bus outside your house and we're going to evacuate you from your home, this acts like a curse, a voodoo, and people genuinely suffer. Establishing true effects requires blind trust, blind trials, and innocent victims, and that was what we will be looking at. The natural science of food and its waste has much to teach us about energy. The energy density of food is printed on the packet. For example, 16,000 kilojoules per kilogram on my biscuits. The amount of fuel and the amount of waste are reduced in proportion to the high energy density. So if we have a sort of fuel which is 1,000 or 1,000,000 times denser, then the amount of waste will be 1,000 or 1,000,000 times less. Controlling the biological waste of humans is a major task, and failure pollutes and supports infectious diseases. We educate children at an early age what to do and how to restrict their social life until they have learnt their lessons. If we had a fuel with 1 million times the energy density, both the fuel and the waste would be reduced to 1 kilogram for all the energy, for all purposes, for the whole of your life. Such an ideal waste and such an ideal fuel would not support infection, be easily contained, and not even smell. We should teach people to appreciate the best possible waste. The laws of nature are extremely simple, though mercilessly strict. The first law is you cannot make energy or destroy it under any circumstances. It has to come from somewhere, and it has to go somewhere. Secondary sources like electricity and hydrogen have to be supplied by some other source from a primary source. So it's the primary sources that we have to concentrate on. The second law of thermodynamics, doesn't matter about the fancy name, concentrations of energy, that is fuel, tend to leak away. Boulders like to roll downhill, water likes to flow away. A hot cup of coffee goes cold, and 2 lukewarm cups of coffee can't be made to a hot cup of coffee. There is a premium on high concentrated fuels. The Earth has been here for billions of years, and most possible energy sources have already discharged and run away. And there are only 2 possible candidates that we've discussed so far. One is wind, solar, and hydro, which are refreshed unpredictably by weather-modulated daily sunshine, and the other is the fossil fuels generated in photosynthesis in ancient times and preserved by geological burial. Those are now rejected because they do not leave a suitable environment. The energy density of hydro comes from the potential energy of the water. It's extremely small. Hydro projects are huge and environmentally destructive. Energy for a whole of one life would take 10 million tons of water coming over a 100-meter high dam, when similar wind energy is delivered by stopping air, by calculating a calculation suitable for a student. It's not difficult, but the answer is the power is very low and wind farms are very invasive. Here is another farm that destroys habitat for fellow creatures and flora too. Use of the word farm is an abuse of language, a cynical distortion. How arrogant is human society to even consider making such mass excesses. Worse, wind and solar are highly unreliable and weak. So then there's the clockwork of food and chemistry and electronics. It's over 1,000 times higher than for the energy density for hydro. But all chemical, food, chemistry, electronics, the energy density is all of the order of 5 megajoules per kilogram, even for high explosives. And you can see here for lithium batteries, hydrogen, they're all in a similar range. They're all what we call chemical. But where is that energy stored? Where is the mechanism? You can't see anything. What do we mean by chemical? In 1924, 99 years ago, a very bright French graduate student suggested in his PhD thesis that all particles, all light, everything should be described by waves. And those waves are now known as de Broglie waves. And it includes light and the same thing for electrons and anything else. it was quickly established by the quantum as quantum mechanics with implied universality for everything. It just needs one sentence. All matter is described by waves with wavelength h over mv, where h is a constant, Planck's constant, m is the mass in kilograms, and speed v is in meters per second. An electron is trapped in an atom, like a sound wave in a musical instrument, has kinetic energy half mv squared. This is chemical or electronic energy. Exactly the same way a proton or neutron trapped in the nucleus has an energy of a half mv squared too. This is nuclear energy. Let's actually work it out. I'm sorry, the picture here is the wrong picture, but you can imagine a wave in a musical instrument. The wavelength of the wave cannot be longer than twice the dimension of the box that the electron or the wave or the musical sound is in. And if you put in that simple algebra, you get a formula for the energy, the kinetic energy of the wave is h squared, which is constant, over 8ml squared. And if we substitute for the electron mass and the size of an atom, 10 to the minus 10 meters, it comes out as 7 10 to the minus 19 joules, 4 electron volts, and in the case of carbon, that comes out at 35 megajoules per kilogram, right in the middle of the range of chemical energies that we saw. In just the same way, if we put in the size of the nucleus, which is 10 to the 5 times smaller, if we put in the size of a nucleus, that is 100,000 times smaller, so the L is 100,000 times smaller, and L squared is 100 million times smaller, and then we divide by the mass of the proton compared with the mass of the electron, we get that the energy of nuclei should be 20 million electron volts. The effect of the changes in M and L in this formula is what has knocked the 20th century, which hasn't quite recovered yet from the reputation of this huge number. There's a difference between nuclear energy, radioactivity, and radiation, and not only experts like you will all become, but also members of the public need to understand the differences between these. The nuclear energy involves the energy of the interaction of a nucleus with a neutron creating fission, or of two nuclei creating fusion. Both are easily controlled by removing one of the components. Radioactivity involves a sole nucleus, and because there's only a sole nucleus involved, it's not controllable, and it emits radiation just once at random. Radiation damages atoms and molecules, not nuclei. Radioactivity and its radiation are not contagious. This is a very important public health statement which is not apparently acknowledged. You cannot catch radioactivity. You can't catch radiation. It's not like a virus or something. Radiation does not make anybody or anything radioactive. Unlike dead tissue, when it has been irradiated, in the days and hours after the exposure to radiation, the tissue reacts to cure the damage that the radiation causes. The whole of cellular biology, in fact the whole of biology, is designed to optimize the survival of life from the oxidative attack by either chemicals or oxygen or radiation that breaks molecules. This is what biology is about. The reaction that it engages after the radiation, it repairs the DNA, replaces cells, and adapts in recognition of future responses to future attacks. The adaptive process is not suitable for description by mathematics because it changes every time the cells are affected and for different cells. Although many researchers spend a lot of time, waste a lot of time, looking at the shape of the effects of doses of different size, it is a mistake, I suggest. Since the energies of life in molecules are often 1,000,000 times weaker than the radiation, how on earth can life and radiation, the biological samples survive? To defend against attack by radiation, oxygen, viruses, etc., life is constantly changing and adapting its protection. But there's a difference, because whereas viruses evolve and change, and we adapt and change, the radiation never adapts. And for 3,000 million years, radiation has hit life in exactly the same way, and life, biology, has learnt how to protect itself by watching the way that radiation works. So there's a question, what is a safe dose of radiation? If you have ultrasound or an MRI scan, you're also affected by radiation, but it's a long wavelength, it's not ionizing radiation. And the effect is to heat the tissue. And that means that in order to have a safe level, all you have to do is have a level of heating which is less than your normal metabolic rate, which is about 1 watt per kilogram. The safety of nuclear radiation, ionizing radiation, is completely different. To kill a tumor, you need ionizing radiation of about 2 joules per kilogram per day. And that is 2 times 10 to the minus 5 watts per kilogram. A safe dose for ionizing radiation, agreed in 1934, the year that Marie Curie died, is about 0.2 milligrams per day, about 2 times 10 to the minus 8 watts per kilogram. So for some reason, nuclear ionizing radiation is much more serious than ultrasound or MRI. The reason ionizing radiation is 50 million times more sensitive than ultrasound or MRI is an effect called the photoelectric effect, which is in fact solved by Einstein in 1905. And in fact, interestingly, this is what he got his Nobel Prize for. The effect of ionizing radiation is not uniformly to heat the tissue or the material, but to cause a very small number of very large interactions, which we think of as particles hitting the material. And this is the photoelectric effect. So although some cells are hit very badly, most of the tissue is not affected at all. And this is very important for the strategy of biological recovery from radiation. Animals are completely unfamiliar. They do not sense the activity going on at the cellular level, and therefore they are quite innocent when in regions of high ionizing radiation. It's only us who know too much and then are too afraid that cause the trouble. To confirm such activity in real life, we need to consider animals, for instance in the evacuation zone at Chernobyl. They have not seen exciting videos of the effects of radiation at Chernobyl. They are quite innocent. And I've read this the picture here, should have appeared earlier, but the statement is. So the animals at Chernobyl seem to be thriving. They're radioactive, but they're fine. They're very glad to see the back of the humans who are taking up their share of the environment. There are some very, very nice videos by National Geographic and BBC and others on the animals at Chernobyl. An important accident occurred in 1987 at a place called Goiania in Brazil, where a very strong radioactive source of cesium-137, one of the principal isotopes of importance at Fukushima, was the radiotherapy was stolen by some scrap metal merchants who thought they would use the steel, and they took it home. The children broke it open. The children liked the bright light ionization that it caused. They had it all over their faces, in the food, across the kitchen. They invited their neighbors in to see what had happened and how exciting it was. They didn't know what they were doing, and 2 weeks later, a geologist who had some radiation measuring equipment diagnosed what had happened. At the end of it, 3 people died, including one of the children, and 70 people were internally affected by the cesium-137. But nobody has died of cancer in the following 25 years caused by the radiation. So what happened at Fukushima in March 2011? 3 separate stories, each with an important message. The first was the earthquake and tsunami. And this, because of the education system in Japan, every school knows what to do when the earthquake hits. They practice it, and it's not a surprise. So it was a triumph of education that everybody knew what to do. 20,000 people died, but society recovered. All the nuclear power stations in Japan were immediately shut down, but there was one which was avoidably and commercially seriously destroyed. The destruction of the 3 reactors at Fukushima Daiichi was a serious commercial accident, but there were no loss of life, no casualties from the nuclear release at all. The third thing that happened was a simply unnecessarily and socially and environmentally deadly evacuation and media-driven excitement, about which nobody knew anything. They were told it was never going to happen, which is a very bad way of teaching anybody. And the panic spread not only from Japan, but around the world, in particular to Germany and other places. And this is still going on now, as you know, in connection with the water release, which I could speak about if you ask me questions. This is all unnecessary. For the last 120 years, we have known the benefits that radiation can bring to life in medicine, curing cancers, finding broken bones, and all sorts of other imaging things. And Mary Curie, of course, blessed us with revealing all of this, but she would be horrified the way we are misusing or failing to use nuclear environment in the environment. It all went wrong in the 1950s, an era of fear and distrust associated with the name of Senator Joseph McCarthy, who suspected that everybody was a communist sympathizer. People were thrown into jail. It was a terrible era of fear around the world, particularly in the US. And in response to that, at this time, the rules on, or the regulations on radiation were tightened up between 700 and 1,000 times so as to supposedly make things safer. But you don't make things safer by just piling caution on top of caution. It didn't make any difference, and it just made people frightened. Whereas sunbathing and skin cancer are a very serious source of damage to bodies from radiation. We do not have the United Nations permission to sunbathe when we go on holiday. And the committees and the regulations associated with ionizing radiation in the nuclear range should be changed. It's useful to try to draw a picture. And the picture we can draw is to draw circles where the area of the circles represents the monthly radiation dose. And the first red circle is the radiation dose that is used to kill a cancer. And that is of the order of 40,000 milligrays a month. The tissue near the cancer, very often the hair falls out, that may be burnt and so on, but usually there is not serious long-term health consequences, and it survives by the mechanisms that I've described. And that's the yellow circle at about 20,000 milligrays per month. The green circle is about 100 milligrays per month. Actually, they say it's about 70, but 100 was my figure, but something like that. This is the agreed safety level of 1934. And we know that nobody at Chernobyl and nobody at Hiroshima and Nagasaki who survived the fire and the blast and received a dose lower than 100 milligrays, the green circle, actually suffered. It's also, the green circle's also shown exaggerated, expanded, so you can see. And in there's a little white dot, which is the inappropriate public safety level, which has been recommended since the 1950s and is causing things like the evacuation at Fukushima. So, as far as the energy problem is concerned, nuclear energy is the only possible choice for large-scale energy use in the long term. But are we sufficiently responsible to reverse the disastrous legacy of the 1950s, taking the matter up to the United Nations as necessary? Big question. Are we clever enough and organized sufficiently to accept the responsibility of a new energy source as when we accepted fire 1 million years ago? We know how to do it, we've done it before, to a more dangerous source of energy. Are we ready to change regulations to teach our children, not just a few experts, but to welcome the benefits of the new nuclear age? I've written 2 books on this subject, looking all the way from the physics and all the way through the environment and the sociology and so on. The first was Radiation and Reason, which is already available in Korean and was published before Fukushima, although the Korean edition has some afterthoughts associated with the Fukushima. And the second is Nuclear is for Life, which has been now translated into Korean and will be issued shortly, I believe. this is the best I can do. It's up to everybody to join together to think of those three things that we need as nature's guests. One is to find out how things work, to look after the environment, and to cooperate with others following the policy through. And that may even involve trusting the Japanese on the subject of water. But that's a particular question that you might want to ask me about.